All right, so as we continue through Chapter 17, Glencoe Science textbook, we're talking about predicting precipitation. So we know about precipitation, right? Precipitation is when we have a solution that kind of falls out or is drawn out of solution. And we talked about when this happens. This happens when we have sufficient concentrations of ions, right, in a compound. And we talked about Ksp and the role that that plays in forming a solid. So if the Ksp, and that is the product of concentrations, let's say of A plus and B minus, just as an example. So the Ksp comes from a product of concentrations of ions, and that would be for when AB dissociates to A plus to B plus, right? B minus here. And if this is a 1-to-1-to-1 ratio, we have ones as our exponents. So we know a little bit about this already, the Ksp. What we're doing here now is we are determining the concentrations of ions that could be a part of a solid, precipitate. So we're going to have ions in solution. We have to find out what the concentrations are. We have to determine what the Ksp is for a proposed product that might be formed. And then we have to go ahead and multiply the concentrations to see if we exceed the Ksp. Because remember, if the product exceeds the Ksp, then we will have a solid that's formed in solution. So there's a couple things that we have to understand. First, I don't know whether these are in your notes here, right, or not, but we're going to have to understand these two definitions. Experimental ion product. Okay, so that's going to be mentioned throughout this lesson here. The experimental ion product is the product of the actual concentration of ions in a solution in a lab trial, okay? So again, the key word there is experimental, and then of course we have ion product. Pretty self-explanatory. So in the lab, you're mixing up, solution A that has a couple ions in it, and solution B that has a couple more ions in it, and we're going to find out what the experimental ion product is for substance, AB, let's say, that could be formed. The published Ksp, and again, I don't know if you'll read this exact terminology in the textbook. This is what I, was trained calling it, the published Ksp, so that's I'll refer to it. And that's simply the Ksp that you find in your textbook or online. And that is the solubility product constant for the substance and usually it's given at room temperature, okay? 298 Kelvin or 25 degrees Celsius. And we can assume that anything we do in the lab is at room temperature, so we'll use those numbers. And so the published Ksp, the previous lesson, right, the last couple days, the product of the maximum concentrations of ions in a saturated solution. So it's the product of concentration of ions in a saturated solution. That's where you get the Ksp. Any product above the Ksp will yield a precipitate in solution. That's been the message the last couple days when we're explaining Ksp, and that's what we're focused on today. So if the experimental ion product is greater than the Ksp, that is the published Ksp. Okay, so experimental ion product here, and I will abbreviate that probably in the future here, just EIP. EIP, experimental ion product, is greater than the published Ksp, then a precipitate should form. This is because the solution is simply too crowded with ions to not bump together to form a solid, right? So remember the example that we talked about the other day. If we have 50 students in this classroom, I'm guessing 50 students in this classroom, we could all stand somewhere in this classroom and not bump into each other, okay? We could even just vibrate slowly, or we could just shuffle our feet, and we would be fine to not bump into each other. But let's say one more student was added, we had 51 in this room, that would be the tipping point. That would be the point where everyone has to shuffle to allow this 51st person in, and somebody would bump into somebody else. And if that bumping would represent forming of a solid in solution, then a precipitate would form. So there's a maximum sort of saturated point. Anything above that means that there should be precipitate forming. So how do we find out if a precipitate really should form? Well, we could mix the solutions together and look at it, right? We could look at it, and I believe in the activity, the lab that you guys did, factors affecting reaction rates, you mixed some solutions together, and you did see that two solutions, clear solutions, when mixed together, formed a cloudy white substance in the beakers, correct? Okay, so that's your precipitate forming, okay, in that lab. Now, we are going to do the same thing in another lab here, but we're going to support what we see with calculations and to see, if we actually should get a precipitate or not. We're going to prove that, and this is how we do it, sort of mathematically. So we find the concentrations of each ion, okay? So find concentrations of each ion in solution. As I mentioned before, we are going to have some ions in solution, A, B, okay? You need to find the concentrations of your ions in solution. Then we need to compare their product, compare the product according to the Ksp expression to, what are we comparing it to? The published Ksp. So compare the EIP to the Ksp, the published Ksp, for that temperature, of course, which will be room temperature for us. So this will indicate whether you have enough ions for a solid to form. Remember, compounds with a low Ksp need only a small amount of ions to form a solid, while compounds with a high Ksp need many ions to form a solid. Okay, so this is more or less, most of this is a review from the last couple days, but the comparing of the experimental Ksp and the published Ksp, that's the new thing, okay? All right, let's talk about some solubility rules, because the Ksps that are listed in the textbook are mainly for substances that are only partially soluble or fairly insoluble, so they have really low numbers. So how do we know if something is soluble if it's not on the list? And you should have some solubility rules in your textbook as well. Let's see. Oh yeah, page 974. So I believe these should be in the notes that I gave you, but also page 974 might be laid out just a little bit differently. I would encourage you to look at these as well. 5 rules. Yeah, they look like pretty identical. Anyways, the solubility rules that you'll find in online or in textbooks should be fairly similar. Some may be a little bit more specific than others, but they should all be pretty close to being the same. Okay, so what are the solubility rules? There are some general rules, like we mentioned before, sodium chloride, that NaCl, like regular salt, that's soluble, very, very soluble. The Ksp is super high, so you won't find a listed Ksp for NaCl. Why? Because it's extremely soluble. Like, trillions and trillions of ions can be in a small amount of solution before anything happens. Like, it's super high. So the first solubility rule says that all common salts of group 1 elements, now salts would be a positive ion and a negative ion generally, okay? So a positive ion and a negative ion. All common salts of group 1 elements, okay, so that's the alkali metals on the far left column of your periodic table, the far left column of the periodic table, and ammonium, okay, so the far left column, that includes, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, and ammonium is NH4+, okay? So if you have, things like this, sodium, potassium, right, all this sort of stuff, etc., and ammonium, they are extremely soluble. You can pretty much guarantee that they will dissociate in solution. You put that powder, potassium, anything, potassium iodide, in solution, mix it around, boom, it dissolves really easily, okay? That's number 1. Number 2, all common acetates and nitrates are soluble, okay? Acetates and nitrates. Do you still have that periodic table that I gave you? On the back, okay, you should find acetate and you should find nitrate, okay? So in your notes right now, look up acetate and nitrate and fill that in your notes here, okay? So make sure you have that paper. It's extremely important that you have that paper that I handed out to you. So page 970 in your textbook here is where you find that ion chart. Acetates, okay, so acetate is a 1- ion. Of course, that's CH3 COO minus. All right, we talked a little bit about this when we did the organic, why that's written that way. The C is attached to the O and then separately to the other O, so the O's are not together. That's why that's written like that. And so if you have any kind of really any acetate with a cation attached to this ionically, then it's going to be soluble. Nitrates as well. So you find nitrates in there. So it's NO2 minus. Okay. So really any compounds with these ions are soluble. Very high Ksp. You won't find a Ksp probably for them. You may find somewhere, but those are soluble. Okay. All binary compounds of group 17. Yeah. Sorry, my bad. Yeah. I think that's NO. Yeah, that should be NO3. Nitrite is nitrite is NO2 minus nitrate is NO3. All binary compounds of group 17. Yeah. That's the halogens. So group 17 is the column, the second from the far right. Okay. And if you have a halogen there, now other than F, so there are some exceptions. Again, remember we talked about chemistry. We talked about chemistry rules for nature. There are always exceptions, okay? Certain conditions, certain things. You'll find as you move through studying more and more science, there are more and more exceptions. So we're hitting the big rules. These are the big rules. 99% of what you're going to encounter will be covered in these rules, and you'll be able to work with the KSPs that are published. But halogens generally with metals are soluble, except for. So if you find a silver ion, a G+, with a halogen, generally, they are not soluble. Mercury, that's mercury 1, so that's Hg1+, okay, with a halogen, not soluble. And lead, so Pb, either 2+ or 4+, with a halogen is generally, now, if it's with an F, you'll have to check the KSP. Okay, you'll have to check the KSP because it's kind of on the bubble there. That's what that means. But if you want to be sure, if it's chlorine or bromine or iodine, these are soluble. Okay, silver iodide would not be soluble. Mercury bromide would not be soluble, and so on. Okay, all sulfates, SO4, 2-, all sulfates are soluble, except if you have barium, strontium, lead, calcium, silver, or mercury sulfate. Okay, so if you have any of these cations, the positive ions with a sulfate, those are generally going to be fairly insoluble. Except for those in Rule 1. So Rule 1 is the far left column, right? Group 1 elements. So anything other than the Group 1 elements, generally carbonates, hydroxides, oxides, sulfides, and phosphates are insoluble. Okay, so most carbonates are insoluble. Most hydroxides are insoluble. Okay, those are the general solubility rules. Again, most of what you're going to encounter, you look at those rules, you'll be able to find it. I don't know if I've given you this chart. No, I haven't given you this chart, but this is an example of a chart that I found online. That solubility of compounds in water. So if you come across something like this, I can kind of show you how this works. These are, ammonium. Okay, look at ammonium right here. These are the cations on the left, and along the top would be common anions. So remember, cations are positive, anions are negative. So ammonium bromide, okay? We generally said that pretty much anything with ammonium is soluble. So look at all the way across here. All S's, okay? Except for oxide. So there's no data on that one. But S is soluble, P is partially soluble, I is pretty much definitely insoluble, and D, it decomposes. So remember the decomposition versus the dissociation. So it's not necessarily going to give you pure ions. It's going to decompose into possibly some other things. And there's not too many of those. Why are there dashes? For a variety of reasons, I guess. They're not able to measure these, or they don't normally form a compound at all. Yep. This is on 974. Thank you. That's the next. Oh, 2 pages over from your solubility rules. 974. That's probably where I got it from. That is correct. Good. Page 974. In your Glencoe matter and change chemistry. So this is, again, there's multiple charts, solubility rule setups. If I gave you something like, lithium oxide. Lithium oxide. Is lithium oxide soluble? What do you say? Page 974? Tell me. Okay, so lithium, so you find lithium down here. So here's lithium. And then oxide is over here, right? So lithium oxide, here's the intersection of those, that row and column. It has an S, so lithium oxide should be soluble. Question?
Yeah, I'm looking at lithium bromine. It has a question mark.
Yeah, again, not every cation will form an ionic compound or a bond with every anion. So,
Okay.
yeah, when you put a chart like this together, right? When you put a chart like this together, it's like, so it's like, how do you react with every other person in this school? Well, some would be good, some would be not so good, some would be, we don't have data for it, right? So if we're talking about the kids in your class, we probably have a better understanding of how you would interact with the kids in your class. But if we have a chart like this, it's pretty all-encompassing, right? And there's what do you do with a spot where you have no data, or where there's, this does not, form, like hydrogen hydroxide. Well, that's water. This is not an ionic compound. So we're not talking about dissociations, is, decomposition of anything but under electricity in certain conditions. So this, you know what I mean, hydrogen hydroxide. You have a hydroxide column and you have a hydrogen row, but certain things are like, doesn't really, it's not applicable. So think about the dash as maybe just not applicable, okay? Lithium oxide is soluble. Lithium hydroxide would be over here. Yeah, not soluble as well. So example 7 in your textbook, this is where the rubber meets the road, as in an old saying. This is where we actually have to put into practice what we've been learning. This is... Are you okay? Are you good? Okay, predicting a precipitate. So the question says, the sample problem says, and I'll just walk you through this sample problem and then you'll get a chance to work on this on your own, but predict whether a precipitate of PbCl2 will form given 100 milliliters of 0.0100 molar NaCl when that's added to 100 milliliters of 0.0200 molar lead 2 nitrate. Okay, so this is the kind of question that you'll see. What do we need to do? Well, we need to find out if this will form PbCl2. Okay? Now, how do we know that? Well, we know that if there's enough lead ions and enough chloride ions, that a precipitate will form. Where do the lead ions come from? Well, they come from the dissolving of lead nitrate. Notice that nitrates, right, generally are insoluble. So if you put this in solution, you'll be able to mix it up and it will dissolve into Pb2 plus ions, right, and nitrate ions. Okay? Now, these nitrate ions are not going to be involved in the question. They're just going to be floating around because what we're interested in is knowing whether we're going to get any PbCl2. So I'm concerned about the Pb2 plus for sure. Over here, we're concerned about the Cl. So this is going to give us Na plus Cl minus. So I need to know not about the Na, but I need to know how much Cl minus we have. So how much lead do we have? How much Cl minus do we have? And when I say how much, we need to figure out concentration. So this is, that's the setup for the problem. And they mention here that these are the ions that we are concerned about. And they are going to come from the dissolving or the dissociation of these soluble compounds. Got it? Okay. All right. So we have these ions floating around in solution. Are there enough of them to form a compound? Well, we have to deal with, first of all, concentrations of ions. So what we're given is we're given a volume and a concentration. Okay. Now this is moles per liter. This is moles per liter, and this is moles per liter up here. We only have 100 mils. That's 0.1 liters. Okay. So how do they go about doing this? Well, we have 100 mils of 0.01, 100 mils of 0.02 of this one, and the Ksp, we have to look that up, and you would find out that that Ksp is 1.7 times 10 to the negative 5. Okay, so obviously that's going to be important. First things first, let's write, just like we did in the last couple lessons, let's write an equilibrium equation, or a solubility equation here. So PbCl2 would be in equilibrium with this Pb2 plus and 2 Cl minuses. Okay, so that's the balanced chemical equation for what would be the phase equilibrium we talked about a couple days ago. Now they write the experimental ion product as the Qsp, okay? The ion product expression, that's what this textbook calls it. I've always called it the experimental ion product. But you'll see the Qsp is the same as the EIP that I mentioned in the notes, okay? So experimental ion product is the Qsp. All right, so here we go. This is maybe the tricky part. I don't know. We have to find out what the concentration is of each of these ions. We have to find out what the concentration is. Question?
Why isn't there
No, you don't do 2 times Cl in there. Only if you're trying to find unknown here, then you have to set up that. We're not trying to find unknown, right? We're not trying to find the unknown. We're trying to use the concentrations that we're given. So we actually can use concentrations here. We're not solving for them. Okay? There's really 2 ways you could look at this. You could solve for this and then find out what the concentrations each are, and then go back and calculate your given concentrations and see if they exceed that. But that's going to be a longer road to do that. It's going to be more work. This is the straightforward way of doing this. You always start with your Qsp or your trial Ksp, okay? The experimental ion product. Can someone grab that door for us, please? Someone near the back. Thank you. All right, so I've got 0.02 molar, okay, of the Pb2 plus. Now, I'm not sure that I really like how they go about doing this, because they've just basically averaged these. There's kind of equal amounts. You see how 100 mils and 100 mils. So the concentrations, they just average the concentrations, really. They divide these concentrations by 2. I will show you a way that makes a little bit more sense, because I don't really have a good way of explaining to you why they did this. I would do it slightly differently. But what you have to do is you have to find out the concentrations here of your ions in solution, okay? So moles per liter. I would find the moles first, and then divide it by the actual volume that you have when you mix those together, which I'll show you that way. But all in all here, let's just work through this. You find the actual concentrations for your lead and your chlorine, okay? And now what you do is you plug those concentrations in to your Ksp expression. You do not just randomly multiply this by 2, okay? We're not solving for x. You use exactly what you're given, and you multiply them together according to the Ksp expression, which would include the squared there, right? So we multiply these, we get our trial Ksp, or experimental ion product. Then what you do is you compare your trial Ksp with the published Ksp. This is the one from the textbook right here. And because this is much smaller, okay, it's smaller, that means a precipitate will not form. If your trial Ksp or your experimental ion product is less than the published Ksp, there are not enough ions to form precipitate. Got it? If this number over here was greater, if this experimental was greater, then a precipitate would form. Okay. All right, let's take a look. Okay, let's take a look here at 25. I'll show you how I would do 25, which is slightly different than the practice problem, but it yields us the exact same. So 25 in your textbook here, use the Ksp values from table 3 to predict whether a precipitate will form when equal volumes of the following solutions are mixed up. Okay. So we have 0.1 molar lead nitrate and 0.03 molar sodium fluoride. Okay. So the question is, first of all, it doesn't tell us which compound we're looking for. So how would we know for 25A, how would we know what we're looking for? Again, these are going to be dissolved in solution, okay? So I'm going to have Pb, looks like 2 plus ions. I'm going to have nitrate ions in solution. I'm going to have sodium ions in solution and fluoride ions in solution. So between these four, what possible precipitate would I be looking for? So that's the first thing you have to figure out here, right? So solubility product constants, okay, on 969. So 969, there's a chart as well as I think in chapter 17 there. So there's another chart on page 969 if you want. So what we want to do is we want to ask ourselves, will sodium nitrate, will these form a precipitate? Is that a fairly insoluble compound? Is this one fairly soluble or fairly insoluble? Okay, very soluble actually, because this is group 1, and this is a nitrate. So we go back to our rules, right? Or you could look on this chart if you want, go back to your rules. Nitrates are soluble. Group 1 elements soluble. So this is definitely not going to form precipitate. Okay, what's the other option? Well, it looks like the other option might be lead fluoride, PbF2. Okay, lead fluoride. Now let's look on our solubility chart there. Okay, where's lead? Okay, I'm gonna have to zoom out here. Lead is right here, and fluoride is it on there? Oh, no fluoride.
Those are only the polyatomic.
Lead and fluoride. Yeah, these are all polyatomic. Okay, that's fine. Okay, so lead fluoride. Okay, F. This doesn't give us too much help. So let's go to our solubility product constant chart. So lead fluoride. Let's see. Fluorides. Oh, lead fluoride. Look at that. 4 times 10 to the negative. That looks like 8. 4 times 10 to the negative 8. Okay, so that is definitely a small number. So, yeah, so this one's going to be fairly insoluble, right? This is the one that we're focused on. And I just read that number, but what was it again here? 4 times 10 to the negative 8? Lead fluoride, I'll find it here. PbF2. Okay, so I've got 3.3 in the textbook here. So 3.3 times 10 to the negative 8. Okay, we'll use that one as it's in your text. So that's the Ksp. That's the published Ksp. Okay? All right, so let's find out if we have enough ions to multiply to greater than this according to the Ksp expression. Well, PbF2 is going to be in equilibrium with, it looks like Pb2 plus 2F minus. That's what that's going to look like. And so the Ksp expression would be equal to the concentration of Pb2 plus times the concentration of F minus squared. And this is super important that you guys can nail this down for the compound in question. Okay, you have to come up with the Ksp, which I would suggest you really need to write this as well. Right, this is what we've done for all these examples. I would write these both down. Make sure you're on the same page. Okay, so we need to find concentrations. That's moles per liter, right? So Pb2 plus, the concentration. Don't forget those square brackets. Some of you are forgetting square brackets in some of your assignments and stuff. That you can't. Don't forget the square brackets. That means concentration. You need those. So the concentration is going to be whatever moles per liter. Okay, moles per liter. And we have to understand equal. Okay, so it says equal volumes. Okay, so we can assume that this is, maybe 1 liter or whatever, equal volumes. So they're equally, and that's maybe why in the textbook that they just kind of found divided by 2 because they're equal volumes always, but they might not always be equal volumes. So lead here. Okay, so we've got 0.1 molar, 0.1 molar, okay, in 1 liter. And for F, we've got 0.03 moles per 1 liter. Okay? If you mix these two together now, watch this. If you mix these two together, whether it's 1 liter or 10 liters or whatever, you're going to be adding the volumes here in our new solution. So this is going to be per 2 liters or 2 units. Okay? So for lead, Pb2+, we actually have 0.1 moles in 2 liters now. You see that? And for F-, 0.1 moles, 0.03 moles per 2 liters. So consider the total volume once you mix the solutions. And the reason why I'm doing this is because you're not always going to have equal volumes. You're going to have different volumes. That's very important. So you can't just go ahead and divide by 2 always. All right? In this case, we're adding equal volumes. So whatever volume this is, we're adding equal volumes. So we're going to get a new concentration. So these are added together. Okay, so then the new concentration here in our new beaker. So think about this. We've got 1 liter of this, 1 liter of this. Now I have 2 liters. Same number of ions, but they're now in 2 liters of solution instead of just each in 1. You get that? So the concentration here is, what is that, 0.05 molar. That's our new concentration with the new volume. And this one, F-, is, what's that, 0.015? 0.015 molar. Make sure I'm doing my mental math correct, someone. So now we're going to look at our trial Ksp, or our experimental ion product. I like trial Ksp a lot, actually. I use that a lot, I guess. But it's going to be the concentration of Pb2+, 0.05, times the concentration of F-, 0.015, squared. All right, so 1.125 times 10 to the negative 5. 1.125 times 10 to the negative 5. We'll keep all our decimal places, that's fine, as we compare, okay? So it's fine to, I mean, sig figs, yeah, but it might be a little tricky. So, well, actually, what are our sig figs? 2 sig figs. We have 2 sig figs. So, I guess probably you should just consider this, because that is our, if it's close, you know, you don't really know what these decimal places are. So yeah, I guess you should use your proper sig figs in comparison. But what is our published? 3.3 times 10 to the negative 8. 3.3 times 10 to the negative 8. Which one's bigger? Yeah. So remember, if you have a larger negative exponent, that's a smaller, right? So the trial Ksp is bigger. So since, and I do need you to communicate this well, okay? So I know what you're doing. It's not good enough to end right here and just say, there you go, Mr. Maxwell, figure it out. You know what my answer should be, I guess. No, please state carefully. Since trial Ksp is greater than published Ksp, precipitate should form. Okay, that would be an excellent, very clear answer. And write it so I can read it. At least at least this legible or neater, please. That's kind of my lower limit, I guess. But anyways, yeah, so since trial Ksp is greater than published Ksp, or if you want to do shorthand, you can do, I guess you could do this. Trial Ksp greater than, this is fine, than published Ksp. If you want to do that instead of the sentence, I'm fine. Then precipitate should form, okay? Something like that. Okay? All right, so that's predicting precipitation lesson here. I've done this one with you. I'll get you to do B and 26 here as well. And we will talk about the common ion effect next day. But this is what you can work on for the rest of this class. Any questions? Okay, so once again, that is a good question. The substances that we start with are going to be soluble because we need to know exactly what the concentration of the ions are that produce. So these are going to completely dissociate right here. They're going to completely dissociate. And so if I've got 0.1 molar lead nitrate, lead 2 nitrate, this is going to produce exactly 0.1 molar lead ion, which is very important for us to know in these questions. So yeah, whatever concentration of the original solid you have, they're going to fully dissociate and give you the appropriate amount of ions. This is 2NO3 in the balanced equation, so that's going to be 2 times 0.1. Okay? So good question. They'll always be soluble. And yes, you'll be able to find initial concentrations of the ions given the initial concentration of the very soluble compound. That's why I went right away to this. Hey, the ion is 0.1 moles per liter. That's why I went exactly like to there right away, because I know that this is very soluble and this is a 1-to-1 ratio with this ion, so I know the concentration of that ion, the initial one.